And the next speaker, Cavecchi, 20 minutes, including questions.
All right. Okay. Well, welcome everybody. It's the second to last talk. I will be discussing what happens during the type 1 burst, how the flame spreads over the surface, and this work has been done in collaboration with Yuri Levin, Anna Watts, and Jonathan Braithwaite. So very quickly, today, this morning, Valeri mentioned very quickly the type 1 burst. What are the type 1 bursts? They are very bright X-ray explosions that take place on accreting low-mass X-ray binaries. They are thought to be generated basically by the burning of the freshly accreted material. We care a lot about type 1 bursts because they are very bright, so you see them very well, and especially, as Valeri has explained, from the timing and spectral properties of the light curve, you can derive information about mass and radius of the neutron star. So we want to use them as much as we can, but to be sure about the result that we get from those fits, we want to be sure we understand exactly everything about the light curves. And everything starts from the rise of the light curve. So the basic idea is that you have accreted fresh material on the surface, but then the star is all approximately about to explode, but it will not explode all at the same time. So you will have explosion at one location, and then the flame will spread across the surface. However, one big problem about this is that the rise of the bursts are very fast, so you expect very fast propagation. But there are considerations that prevent basically the flame propagation to be driven by a detonation. So the main problem, the main conundrum is, how do we get something which is gentle like a deflagration but still propagates extremely fast on the surface of the neutron star? I will show you here the movie. So basically, this is how we think. That would be how we think that the flame propagates across the surface. This is a cut, a vertical cut through the burning ocean of the accreted material. Horizontal axis is the surface of the star, and vertical axis is the radial direction. Color scheme is basically temperature. So fluid that is orange is burning, is being heated, and fluid that is blue is cold. One thing that you should note is that there is a clear interface between the hot and the cold fluid. And if you notice, this interface, as soon as the flame has been set up, is always the same. It doesn't change. The dots that you see are simply tracer particles that will help sort of understand how the fluid moves, but mostly you see that there is motion along the interface. So to go quickly to the point, basically one of the most important ingredients in this flame propagation, in this mechanism, is the Coriolis force. Here I plot the contour of the velocity of the fluid coming out of plane. So the idea is that the fluid has ignited at some point on the star, heated up, went up, it's expanded and moved sideways. But then what Coriolis force does, as does it with hurricane on Earth, it stops this motion, starting the motion perpendicularly out of the plane. So basically start a hurricane around the neutron star. Around the flame, which eventually propagate. Now, how does this help getting very fast propagation? It's basically a balance between time scale and length scale, and basically it's geometrical effects. So the Coriolis force has blocked your hot fluid, preventing it to completely spill outside, and you are with this slanted interface. This fluid is hot, this fluid is cold. And then what goes on is simply good old-fashioned conduction, which is slowly heating the fluid below it. So this is good. We said we don't want a deflagration, a detonation, because we cannot get it. Okay, this is conduction, this is a deflagration. This process is relatively slow because it's conduction. But then the fluid heats up, it expands, and then it spills sideways again. The spilling sideways is very fast. It's basically velocity given by gravity waves. But this system spins at hundreds. My simulation here are done with 450 Hertz. So very fast. Coriolis force is strong and fast. So by the time the fluid has expanded, Coriolis force immediately acts, recreating the same configuration as before. This gives you an interface which is always the same and keeps on self-replicating. This allows you to have a long surface across which you can conduct. That means, because at the beginning people thought, oh, maybe if it is conduction, if it is a vertical front, this speed will be very slow. But if your front is like this, very horizontal, then you have an increasing factor which is given basically by the ratio of height versus horizontal length scale, and this would be 10 to the 4 versus 10 to the 2, say, centimeters and centimeters. So you have basically a boost of 10 to the 2 from the speed given by the simply a conductive flame. And this gives you already velocity flame that are in good agreement with the observation. Coriolis force here plays another very important role, because I just told you that a vertical front would be slow, very diagonal front is fast. But then you may say, well, a completely horizontal front would be even faster in a sense. So if I let my flame, my initial hot fluid just simply spill across the surface, that would be even faster. The answer there is probably no, because you start with a little region which is igniting, and if you dissipate that heat all across the surface of the neutron star too quickly, then you kill the flame. So actually Coriolis force is very nice because it gives you this confinement, but let's say it doesn't exaggerate in this confinement and gives you good agreement with observation. But then if we play with different direction of propagation, so for example, if you check propagation in this direction, constant Coriolis force, you get some value for velocity, which is good. But if you try to go from pole to pole, because you want to engulf the full star, then you suffer from changing Coriolis force. And basically what we see in simulation is that anyway the propagation, despite being in relatively good agreement, would be too slow. But then, of course, we see, well, we put almost all the ingredients, all the physical ingredients we have on these systems, but we didn't put the magnetic field. And that's what we did. So we started doing simulations, putting magnetic field in the systems, but we didn't play with the value of the magnetic field in the sense that we didn't fine-tune the magnetic field value. We just used the values that we think we see in this kind of system, in millisecond spinning low-mass X-ray binaries. And then we see that if you start with basically the lower end of the magnetic field, you see an interface which is roughly the same. Here the fluid is bending the magnetic field lines. The magnetic field lines give you some kind of back reaction. And if you, well, you didn't see it, but if you check the speed, it's actually going faster. If you increase magnetic field, configuration of flame changes. There are actually here we see a lot of instability going on, but the flame goes even faster. Eventually, if you put it too strong, the magnetic field, so this would be the highest end of the magnetic field that we see in the systems, you see the configuration is very similar to what we see without Coriolis force, but actually if you check the time, this is the speed of this flame is actually slower. So again, to make a cartoon that explains what goes on, is that this I'm plotting cold fluid, hot fluid, okay? This thin line is the magnetic field. And basically the role of the magnetic field, despite the fact that this field is not as strong, for example, as that of a magnet are, is that it's providing me with the little mechanical friction in the vertical direction, which is balancing the effects of motion, of expansion, and of Coriolis force, that gives me exactly, or almost exactly, the speed I need to match the observation. And you can see this. So if I put a very weak magnetic field, well, nothing really changes because it's not enough to block the expansion in this direction. And when you start the hurricane, you would be winding the field lines, but eventually would start to back react because of tension. That's where the friction comes from. But if the magnetic field is too weak, it needs to be stretched a lot before it can back react. The flame has already passed. It doesn't have much influence. On the other hand, if you increase it enough, then, okay, we start the hurricane because of Coriolis force. I'm stretching magnetic field. Tension back reacts in a shorter time scale because magnetic field is stronger. That limits the speed of this hurricane. That limits the confinement by Coriolis force. And my interface will become more horizontal, gives me much of this geometrical factor. My flame goes faster. Of course, you see where I'm going. If I put too strong of a magnetic field, I will not be able to generate any kind of hurricane structure because the magnetic field back reacts immediately, but actually it doesn't matter because already also in this direction, the magnetic field is blocking the fluid. And so I can get kind of same inclination or even more vertical front, which would be slower. We tested this basically doing simulation with different values of magnetic fields. Ignore for a moment the red dots, red squares. The horizontal line here is the velocity of the flaming if you do it for a 450 Hertz rotating star without magnetic field. And you see that if I increase the magnetic field, the velocity stays the same, eventually goes up, when basically the two forces start balancing each other. Coriolis force, I mean, the time scale basically of reaction of Coriolis force and the time of the friction given by magnetic field balance, I reach the top, and eventually I'm completely dominated by the magnetic fields and the speed goes down. We did the same for a very slowly rotating source, this one at 11 Hertz, because this is a very important source, so we wanted to see what happens there. And again, you see that for very high magnetic field, the speed is completely dominated by magnetic field because the Coriolis force is useless here. And you see that the velocity agree completely in the two cases because it doesn't matter what the Coriolis force is useless. But if you reduce the magnetic field, the slowly rotating star actually keep following the same trend. This speed would be slightly like going like v to the -1, while the faster rotating star, the balance between the Coriolis force and the magnetic field goes on the side of the Coriolis force, and you get very high speed. Summary, I hope I'm in time. We now completely understand what's the physics necessary to explain the flame propagation in neutron stars during the type 1 burst, and actually the answer is you need all the physics available. You need the conduction, you need the Coriolis force, and you need the magnetic field. And also you saw there was this little motion of fluid along the interface. That is also important. That is due to the fact that the interface where the temperature changes kind of abruptly between hot and cold fluid, that becomes baroclinic fluid, and there is kind of instability going on. So when you put all this together, you get correct speeds. However, this simulation has been done in 2 dimensions. As we see also with Kyle just a minute ago, if you go to 3 dimension, troubles may start. For example, there may be instability going on, and we expect instabilities. Now the question that still remains to be seen is whether this instability will have effect on the flame, for example, making it faster, or maybe killing it because of disruption of the flame. But once we fixed also the last detail, then at that point we will be really in the position to be able to simulate ignition at different position of the star, different configuration of magnetic fields, and so on. We explore the full parameter space, and then we will be able to simulate first the full propagation, and second, basically simulate the evolution of the emitting pattern on the surface. And once you know the emitting pattern, you can do all the things as well that I mentioned before. So using, for example, the timing properties of the light curve, because if you have a pattern, your light curve will be a little bit oscillating. And through that, you can measure, taking into account relativistic effects, you can measure mass and radius of the star, which will help eventually to measure equation state.
Much. Questions? Sergey.
When we try to simulate flames, deflagrations, type 1a thermonuclear supernovae, the main problem is the turbulence which develops in shear flows. On one hand, it accelerates our flame, on another flame, it hinders good 3D simulation. What are your Reynolds, Rayleigh numbers, and so on? Do you ignore this completely, or can you estimate?
Yes, so one question that we have and we want to explain is, for example, you saw the interface is like this. The idea is, would, for example, Kelvin atmosphere, the hurricane, for example, is very sheared. The velocity changes in the vertical direction. Well, quick answer is we have to try that in 3D. Longer answer is what we expect is, for example, Kelvin atmosphere may develop, but we also expect maybe that to self-regulate. So, for example, you would hear the transitions was very sharp. It may thicken the flame front, but eventually we think it will self-regulate, therefore sort of adjust, we hope.
More questions? Yeah, Jason.
I have a much more naive question. So it seemed like your simulations, you were starting with basically a hockey puck of material, equal thickness out to some limiting radius. And you want to get at something very, very subtle, and you want to eventually use this to determine the equation of state. But how reasonable is that assumption? Because you're talking about how the flame propagates in time, but how well do you know what the reservoir of fuel looks like to start with?
Yes, yes. So as I said, yeah, that will be a little bit model dependent as well. What you expect is the fluid to be all close to ignition point. So, for example, how to set the ignition latitude, that is a little bit tricky. There are considerations that you can take, depending a little bit on the rotation, for example, of the star, and on properties of what you think is the burning regime. You may have, you can make estimate, for example, where the latitude of most likely ignition is. People think it's at the equator, but that depends on the spin, for example, of the star. And for the rest, you assume the rest of the fluid to be sort of all homogeneous, close to ignition. Does it answer?
Yeah, thanks.
Okay.
Thank you. More questions? Comments? No more questions? Then let's thank the speaker again.